Welcome everybody. I'm Giuseppe di Blasio, and today we are going to explain the very basics of density functional theory. So let's just start with a quick introduction on what DFT is and what it's capable of. We can start saying that DFT is a quantum theory, and it deals with many electron systems, such as atoms, molecules, and solids. The final aim of DFT is to describe the properties of this multi-electron system. For example, vibrational properties, or structural, or magnetic. Another important thing to say about DFT is that people who work with DFT are not like experimentalists that, for example, just stay in a lab, work with laser, and giving some experimental results. But they are people who work with computer, and in particular with software. They do a lot of calculation to have an algorithm that converges to the exact solution. But between them, there is a huge collaboration, and quite often, experimentalists just ask to DFT people, for example, to find unknowns or test theories. And just to have an idea or what can be a main question, this is an example in field of semiconductor, and where the question is if a particular material has a direct or indirect barrier. Most of the picture that I took for this presentation came from materialsproject.org. This is a very user-friendly website, and this is the homepage, and it has a huge dataset of DFT calculation. And for example, if we type silicon on the homepage and we search it, we will find a list of all the DFT calculation of that material, and they are ordered from the most reliable. So if we choose one of these, we will find all the physical properties that came from DFT calculation, like the structure or the phonon dispersion and so on. At this point, I have to introduce to you the detail of DFT, and in particular, the degrees of freedom problem. Because since we are dealing with many electron systems, we have to work with the Schrödinger equation. And as we know, the Schrödinger equation gives us two outputs that are the total wave function and the energies. But now let's just focus on the total wave function. That is a function of all the degree of freedom of the system. This is an example to be more clear why working with the total wave function is not so simple. Because if we have to describe the properties of this L nanocluster that is made around 100 atoms, with simple calculation, we have to solve a Schrödinger equation that is roughly 25,000 dimensional problem. So now it's more clear why working with the total wave function is not best choice. Instead, in DFT, we can redefine the problem in terms of the electron density. That is a function of only 3 degrees of freedom. So this is a huge simplification of the problem. And we can obtain the same information, and this is the main concept of DFT. We don't work with the total wave function. We just work in terms of the electron density. At this point, I have to introduce to you the origin of DFT. And in 1927, Thomas and Fermi just introduced a model where it's possible to describe the total energy of a system in terms of the electron density. But in this case, it was possible because we were in the approximation of consider electrons as non-interacting particle in an homogeneous gas with constant density. And 3 years later, Paul Dirac just added the term that takes into account the overlap of the wave function, the interaction energy due to the overlap wave function. That is called the exchange correlation term. So this is the starting point of DFT.
Okay, now we will enter in more details of the DFT. What is DFT based on? DFT is based upon 2 theorems that were first proved by Hohenberg-Kohn in 1964. The first theorem says that the ground state energy is a unique functional of the electron density. And the second theorem says that the electron density that minimizes this energy is the exact ground state density, electron density. and which means that it solves the Schrödinger equation, and so it's really quite important. And the fact that we have to minimize the total energy gives us the intuition that probably the variational principle is important. And as a matter of fact, these two theorems are demonstrated through variational principle. The first approach to solve this problem, to solve the problem of finding the electron density, was made by Hohenberg and Kohn themselves. And they thought, let's just consider each possible interaction. Let's just write the functional considering each possible terms. And so they consider the kinetic, the electron-electron interaction, and the ion-electron interaction, and a possible external field in the external potential. And doing so, they thought that we will arrive to the exact solution. Well, yes, but actually no, because there is no known way to express the kinetic for a generic interacting system, to express the kinetic energy and the electron-electron potential interaction as functionals of the electron density. The only known way is to revert the classical expression in which we write that, for example, the kinetic energy is equal to the bracket of the wave functions and its quantistic operator. And so we could use some approximations if we were dealing with functions. And for example, it would have been the Born-Oppenheimer and the Hartree-Fock. In the Hartree-Fock approximation, it would appear the Hartree operator and the exchange correlation operator. What is the meaning of these two terms? The Hartree potential is the potential that the single electrons feel due to the fact that all the other electrons, and it's a mean field. And the exchange correlation potential is due to the fact that the electrons are fermions and must obey fermionic rules, such as the Pauli exclusion principle, and the fact that the total wave function must be antisymmetric. And so we arrived to the second approach to solve this problem, which was made by Kohn and G.L.E.M at around 1966. And it's really important because it gives a recipe to calculate this electron density. And they used a similar approximation to the one of Hartree-Fock because they decided to consider the generic interacting system, electronic system, as a fictitious non-interacting electronic system. And by doing so, two terms that are similar to the one of the Hartree-Fock approximation appears. And these two terms, now we have to, due to the second theorem that we saw before, we have to minimize this functional. And by minimizing it, Kohn and G.L.E.M arrived to a formula, and they postulated that this formula at which they arrived were equivalent to just writing n, where n is the number of electrons of the system, one electron Schrödinger equation, in which the potential is an effective potential that can be written as a sum of these three terms. By doing this, they solved the problem of expressing the kinetic energy as a functional, because now we have just written its quantistic operator instead. And they also the problem of expressing the electron-electron interaction, because now we have just replaced it with the Hartree potential. And all these terms can be written as functionals of the electron density. And so the problem is almost solved. But all the things that we didn't know before, we still don't know. And Kohn and G.L.E.M just simply pushed everything that we didn't know inside this term of the exchange correlation. And now this is the main problem of the modern DFT, finding a good approximation that for this term that allows us to reach a proper conclusion, and at the exact conclusion. And now we arrive to the fact why this Kohn and G.L.E.M scheme is Kohn and G.L.E.M approach is important. The fact that let's suppose that the previous unknown term is known. The previous exchange correlation term is known. What we have to do, Kohn and Sham says that you have to try with a trial electron density. Now you have to solve their Schrödinger equation and reconstruct the electron density, and now you just have to compare the electron density. If they are alike, you can stop, the method converged. Otherwise, you have to restart from the second point.
Hi, I'm Edoardo Boati, and I will show you how to deal with the exchange correlation functional. So, in the image, we can see the possible approximation. The exchange correlation functional is the core part of DFT, like we saw before. And in the image, we can see the possible approximations for this functional in DFT. In particular, at the bottom, we have the R3 method that is characterized by the fact that the exchange correlation functional is put equal to zero. And at the bottom, we have the exact solution. In the middle, in the ladder, the higher we go, the better is the accuracy we reach, but also the computational cost will increase. So in this presentation, we will focus on the two most widely spread approximations in DFT, that are the LDA, local density approximation, and the GGA, generalized gradient approximation. So, local density approximation. The physical meaning behind the local density approximation is treating the system locally as it was a homogeneous electron gas. So, for example, if we see the system that is a strongly inhomogeneous system because the density of electrons varies a lot, with these approximation, we fix our attention on a point R in the space, and we approximate the density of electrons around a range dr, around this point, with a constant value that is equal to its value at the point R. So we see that even if the system is strongly inhomogeneous, locally the density of electrons is homogeneous. So mathematically, this can be done with that integral that comprehends the density of electrons and the exchange correlation energy density that we don't really care about. We just say that the term can be split into two parts. The first one is the exchange energy density, for which we can find an analytical form. And the second one is the correlation energy density, for which we need some numerical methods, like, for example, quantum Monte Carlo. Okay, so what are the pros of the local density approximation? The total energy of the molecules and some lattice constant of some simple solids are found with pretty good accuracy. But at the same time, the atomization energies are too big. The majority of negative ions are not even stable with this approximation. And in general, it's not accurate enough for some chemical applications. So what we do next? The logical step beyond the local density approximation is to consider the variation of the density of electrons. And this can be made by considering the magnitude of the gradient of the density. So this is called gradient expansion approximation. But it turns out that if we just consider the information of the gradient of the density, we get worse result with respect than the LDA. So this is surprising, but why is it so? It's because of the exchange correlation hole. What is the exchange correlation hole? We know that electrons interact with each other, and in particular, if we fix our attention on a certain electron, we know that the density around this electron is lower because of the repulsion between electrons. So this phenomenon can be considered by calculating a probability to find a couple of electrons in a certain region of space. And this probability is called the pair density, that is that one. That depends on two important parameters that are the exchange density, electron density, and the correlation electron density. Now, we don't really care about these two parameters, but we care about these three properties that these two parameters must follow. These are really important properties because make us understand why the LDA, even if it is a quite simple approximation, because the density of electrons is homogeneous in this approximation in LDA, it is, however, a good approximation. In fact, the density that we find with the LDA does respect all of these three properties, and but the density that we find with the GEA does not follow the first one and the third one. So this explains us why the GEA is worse than the LDA. So what we do? We still want to exploit the information of the variation of the density of electrons. So that is the gradient of the density. But in this case, we use the generalized gradient approximation. That is the next step. In this case, we impose to the density of electron to follow all the three previous properties. And this can be made with this formula that comprehends the density of electrons, the exchange correlation energy density, and a function that depends both on the density of electrons and on the gradient of the density of the electrons. However, there are several different possible parameterization for the GGA. So it's difficult to give you a general picture, like for the LDA, of the performances of the GGA. For example, if we choose a specific parameterization of the LDA, we could be able to find some properties of a certain material with a good accuracy. But at the same time, we could also find other properties with not so well, with a worse accuracy. But still, it is important to say that the GGA is, however, a better approximation with respect to the LDA.
Hi, I'm Matteo Venturelli, and now I will explain to you the final thoughts about DFT, starting from the pros and cons of this theory. This method of solving a Schrödinger equation has a relatively low computational cost when compared to other methods, such as R3-Fock, and yet shows really high accuracy of around 1 millielectron-volt per atom on average. On the other hand, DFT is unable to estimate correctly the ground state energy and the electron density whenever dealing with intermolecular forces. And in addition, DFT often underestimates the semiconductor band gaps. In order to overcome these problems, it is possible to implement some semi-empirical models for either the van der Waals interactions or the semiconductor band gaps. In these graphs, we can see the performance improvement related to the model refinement. As you can see, the points obtained after the van der Waals correction better fit the Lennard-Jones potential, and those obtained after the semiconductor band gap correction better fit the experimental data. This addition allows to find with great accuracy the physical quantities we were unable to estimate correctly before, at the cost of increasing the computational time of the calculation. The question now is, now that we have the ground state energy and the electron density, how do we obtain information about the material properties? Fortunately, several theories have been developed with this purpose, and the most established one is the quantum theory of atoms and molecules, also called QTAAM, which helps to find the topological and electrical properties starting from the electron density of the system. The topological approach of QTAAM leads to an exact partitioning scheme, in the sense that the electron density at any point in space is necessarily attributed to one atomic domain, which is defined as a region in space in which all electrons are bound to a specific nucleus, as we can see from this image. This theory also helps to find some electrical properties, also starting from the electron density. Thanks to other theory, it is possible to obtain information about the intermolecular interaction energies, crystalline electric properties, magnetic behavior, and so on. This made DFT a really popular theory, especially in the fields of solid-state physics and chemistry, in which the study of the electronic structure is mandatory. Here we can see a lot of applications that DFT can have, ranging from catalysis to photonics, for example. Even though the first steps of DFT were made in the 1930s, the first density functional calculations were performed only more than 40 years later, in 1976. And this is because at the time there was a lot of skepticism, and for convincing reasons. For example, approximations to the exchange correlation energies are unavoidable, and their usefulness can only be assessed by trying them out. In addition, there was no systematic procedure for refining DFT results. All this changed in 1991 in Menton, which is in France, thanks to the 7th International Congress of Quantum Chemistry, in which several density-related methods were discussed in detail, and communication between their proposals improved. As we can read from this citation, DFT methods outperformed the correlated ab initio methods, which are computationally more expensive. As we can see in the graph, in 1991, there was a huge bump in the number of DFT publications per year, and from that year on, this number grew more than linearly, showing the increasing interest in density functional theory. DFT also helped to explain several physical phenomena, one of which is superconduction in graphite intercalation compounds that are also called GICs. In this article published by Nature, the authors explored the architecture of states near the Fermi energy and identified some characteristics that were common to all GICs. All this was made thanks to density functional theory in the framework of the local density approximation. Analyzing the band structure of these compounds that are obtained through the intercalation of several elements, such as lithium, calcium, and ytterbium, as we can see from this image, the authors discovered that superconduction in these compounds is strictly correlated to the occupation of an interlayer state. Thanks for the attention.